All right, are we ready to start? Okay, thanks. So I only have a few minutes to talk here, so I'm going to jump right to what's the most important point in my opinion, and that is my postdoc is winding down, and so I'm going on the job market. So if you like my talk, please tell your colleagues, tell everyone, and if you don't like my talk, let's just keep that to ourselves, all right? So on to the second most important point. What we're really focused on here is any kernelized learning method. So any model where you're using kernels, kernel SVM, kernel logistic regression, kernel density estimation. As a bottleneck in this sort of a method, you're going to have this n-by-n matrix of all the pairwise kernel interactions, right? So ultimately, you're going to be looking somehow at the interaction between every pair of your data points. And the data points themselves live in some RD, where D may be very large. That's the number of features. And for concreteness in this talk, let's just focus on the kernel that's a Gaussian, right? So a Gaussian kernel, I've given the formula here, depends on some bandwidth parameter h. Okay? So in data points, n squared matrix that we have to form of all these kernel interactions, how are we going to approximate this efficiently? N squared simply doesn't scale. All right, well, the first thing that you think of if you have a big matrix is if we can factor it in some low rank way, then we're in business, right? So if we can take this n by nk, express it in terms of some r columns, then with n times r work, we can apply it to vectors. We can invert it more efficiently, all these sorts of things. So this is great. And in fact, these kind of go by the name Nystrom algorithms a lot of times in the machine learning literature. And there are some very good ones that work with order n times r square work. You can do randomized algorithms and things. But the main point I want to make here is no matter what you do, any global factorization like this is going to be limited to error that is at best the biggest singular value you left out. Just because the SVD, we can't beat that. So we know that we have an error that's proportional to the largest singular value we left out in the best case. So remember, we're talking about this Gaussian kernel function. It's got this parameter h. And we're talking about a method that works well if the matrix is low rank and not if it doesn't. Well, how does this h affect the properties of our kernel matrix? So here I've plotted on the left two Gaussian kernels for sort of extreme cases. On the top is a very large value of the bandwidth. On the bottom is a very small value of the bandwidth. So we see on the top, this thing almost becomes a constant function. And if we picture what that means in terms of the n by n kernel matrix, it means almost all the entries are the same number. So in practice, that means it's very low rank, right? The one I've drawn here is rank 1. On the other hand, if we look at this other extreme where h goes to 0, then we have, well, almost a delta function, which means our matrix is almost just an identity scaled by something. So in that case, we're definitely not in a low rank situation, right? Well, so is this really a problem, right? So you say, okay, well, maybe these Nystrom methods, they're not going to succeed in this lower case, but maybe that's trivial. So here's a very simple experiment that we put together. And all we're doing is a Bayes classifier with KDE. So we use KDE to estimate the likelihood of both classes, and we assign the point to the class with the more likely one. I'm not claiming this is the right way to classify data. It's just a toy example. So we have 3 data sets here. The CovType and SUSY are UCI data sets. MNIST is handwritten digits. And what we've done is looked at Gaussian kernel KDE for a very narrow range of bandwidths. You can see here the CovType, these first 4 are just 1 order of magnitude. And you can see that you really get some very different classification accuracies depending on where you lie in these regimes, right? So you can see if we really stopped at 0.35, we'd be stuck at 71%. If we go all the way to 0.02, we get 95%. So what I'm arguing is, and what I'll show a little bit later on, is up here, we are in a low rank regime. With this 1 order of magnitude difference, we've already gotten to a full rank regime. We're already in the position where these Nystrom methods will fail. And I'll show that numerically a little bit later on. Okay. So there's the problem. We've got this method. It only works for some bandwidth regimes. What do we do about it? So in this paper and a couple of other papers, we present a new algorithm called ASCIIT. ASCIIT stands for Approximate Skeletonization Kernel Independent Treecode. All right, so what this does, I'll go through it very briefly, but it approximates kernel matrices that still have full rank in an efficient way. And in this paper in particular, the one at this conference, we compare it to these globally low-rank methods, and I'll show a couple of slides on that in a minute. We also present a new theoretical error analysis that isn't well-suited to a 17-minute talk, but it's in the paper, and I will show just one taste of the results. And then in our other work, we show a scalable parallel implementation. So at the end, I'm going to flash results on 32,000 cores of Stampede. So when I say scalable, I really mean it. All right, so let's jump into the meat of this. So I said it's a tree code. What is a tree code? So treecodes, or fast multipole methods, are kind of a family of methods that come out of computational physics or computational science. And the idea is, instead of on the left here, I've shown this Nystrom globally low rank idea. Instead of doing that, we're going to partition the matrix into blocks hierarchically. And we're going to say that some of these blocks belong to what's called the near field. I've shown them in red. And those are full rank, and we can't do anything about them. So we'll just evaluate those exactly. Some of the off-diagonal blocks here I've shown in green we'll call the far field, and those we can approximate. So rather than a single global approximation, we're going to do some hierarchical approximation that only handles off-diagonal blocks. So that's great. So problem solved, right? Look back into the 80s, use one of these methods. The problem is these don't scale with the dimension d. So these original methods were really invented for physics problems where the physical world is d equals 3. And d equals 3, they work wonderfully. Since we're machine learning people, we're interested in d equals 1,000. And there's two really main reasons why these break down. One, this far decomposition traditionally is done with some analytic series expansion, and that scales exponentially with the dimension. Two, this partition into near and far, the names are suggestive, it comes from distances. Now, when you get into d equals 1,000, you're into a concentration of measure kind of regime. You wind up with all of your pairwise distances become fairly close together. So it becomes difficult to formulate a criterion that leaves a few points in near and the rest in far. So how do we overcome these two problems? Remember, we've got these off-diagonal blocks we can't factor, and these on-diagonal ones we can't separate. So I'm just going to give, very, very briefly here, a rundown of how ASCII works. So there's 4 major steps to our algorithm. One, we're going to need nearest neighbor information, and so that plays a really big role later on. So any method you like to compute or approximate the k nearest neighbors of every point we'll use. We use a randomized tree search in our implementation. Then you construct a space partitioning tree, so you're just going to bin nearby points preferentially, and then these 2 steps I'll emphasize here are we construct an approximation of each matrix block bottom up, and I'll illustrate that in just a second, and then we evaluate from the top down, and I have an animation for that as well. So how do we build these approximations? So remember, we're in one of these off-diagonal blocks. We want to build some low-rank factorization of it. Now that corresponds to, in our tree, we have here some set of points. So we want to approximate the interaction of that set of points with all the other points, all the distant points. So what we could do is factor this small number of points by very large matrix directly, but that scales within, it's not going to work. So instead, we're going to subsample. Now, what we'll do is we'll use the nearest neighbor information to bias our subsample. So we're going to preferentially select rows or select points corresponding to interactions so that we get nearest neighbors more often. And the reason we want to do that intuitively is we expect the nearest neighbors to form the largest rows, the rows with largest norm, and those are going to have the most influence on the spectrum of the matrix we're trying to approximate. Now we'll also fill in some uniform samples as well to make sure we cover everything. So now instead of the interaction between the purple and everything, we're just going to form the interaction between the purple, the nearest neighbors in red, a few points in blue, and now we're just going to factorize that matrix. And so we'll do a pivoted QR factorization. We can form what's called an interpolative decomposition. For our purposes, all that matters is we'll express all of these points in a basis determined by a few of them. So we'll express them all with some effective charges. No, I don't want to do that. Sorry. So we'll express them all just in terms of a couple of others, right? So we select a skeleton, we call it, out of this node, and then we express the rest in terms of it. And then moving up the tree, we just merge these. So one level up, the parent of this node we just looked at and its sibling will again say, okay, we want to compress this basis of now 6 points we have. We'll take some nearest neighbors, we'll take some uniform points, we'll repeat that. Okay, so this is just a reduction up the tree, leaf to root. So on the way down, all we need to do is evaluate. So this is where we look at near, we're going to do exactly, far, we're going to do approximately. And the key to our method is we're going to use this nearest neighbor information again. So you remember before I said that, well, when you try to split near and far by distance and high dimensions, everything's the same distance and it doesn't work. So now we want to evaluate one row of this matrix vector product that corresponds to the interaction between one point and all the rest. So we have its 3 nearest neighbors here in the boxes. And what we're going to do is say that any node that contains the nearest neighbor is near, any node that doesn't is far. Very simple. So we come down the tree, we say, well, this top level node, it doesn't contain any nearest neighbors, so we'll evaluate it approximately. We approximate its contribution with just the interaction between our target with the star and these 3 points. Likewise, we come down, again, here, here. None of these contain nearest neighbors. We approximate all of them. And then at the end, we have 2 nodes left that do have nearest neighbors, and that forms our near field. All right, so that's way too fast for an algorithm that took me a long time to come up with, but I think that's all I can do in the time. What I want to do now, I promised you one slide on the theory that we present in this paper. So recall that I said for these Nystrom methods, the best we can do is sort of the largest singular value we left out. And there's a whole body of literature. There are a lot of really good papers that talk about how to bound this constant and what it means in terms of the sampling methods you use. What we prove that's new in this paper is that the error in our askit method depends on the singular value of the largest block that we tried to approximate. So the key difference here is that this k, if you think back to the example of the very thin kernel, can be full rank. But as long as these off-diagonal blocks aren't, then our method will achieve better error. Now we pay a penalty for that in terms of a log n factor here that comes from using the tree. So there's some trade-off that you need to look at, well, where am I hitting this full rank regime before one method outperforms the other? So I also want to mention briefly the complexity of the algorithm. So the storage cost here, k is the number of neighbors, s is the rank of approximation we're using, and there's an adaptive version of the method which chooses that online. You can just plug in the largest one here. N is the number of data points, p is the number of distributed machines. So the storage is just k plus s squared n over p, so linear and n, it divides nicely across machines. The factorization, so this is the bottom-up step. This is constructing the matrix representations. We have this n over p term, and you wind up with another log p term. There's a reduce over the distributed nodes. And then the evaluation scales as n log n over p. We have a paper coming out if anybody wants to go to supercomputing to see me talk again. We do an order in version of this that I'll be presenting there. Okay, so I've sort of given you this problem that hopefully you believe is a problem where, well, if we look at a thin kernel, then we wind up with a full rank matrix and we can't approximate it. I've given you a new algorithm that can approximate it in that case. But you may still be asking, well, does this ever really come up? Okay, so you recall that table I showed earlier where I sort of flashed a couple of bandwidths and said, well, you get 1 order of magnitude change in the bandwidth leads to some big differences. So here's a little bit closer look. What we're looking at here, this is the cov type data set. In gray, these columns are estimated L2 error in a matvec. So we're just looking at the error of our approximate matrix times some vector and seeing how well we captured that relative to doing it exactly. So the top here is Nystrom methods, the bottom is our method. If you look at this 0.35, which earlier I claimed is a low rank setting, you can see that for both cases we get about 3 digits relative error. Great. And actually, if you look, Nystrom's a little bit faster. Great. So there you go. There's no problem. Divide it by 2, now we're just half as wide a bandwidth, and suddenly Nystrom has 1 digit of relative error, and we're still at 3. If you go down to this 0.02, which in our sort of toy example was the best classification accuracy, you see Nystrom gets basically no accuracy at all. It's nearly 100% error, whereas we get very small error. Nearest neighbors capture most of the interactions here. So my claim is, even if your true bandwidth, so you have your data, you have your model, you have your kernel, you do all your cross-validation, and your true bandwidth is out here, you need to have looked at this one. I don't believe that you did cross-validation if you didn't look at true bandwidth over 2. And if you're using a method like this, then you're not getting enough accuracy to really see what's going on. And to illustrate that a little bit more, we look at another example where we embed our method in a kernel logistic regression. So here we've got 3 methods. This mecha is like a block Nystrom method that's fairly recent. If you're familiar with it, we throw it in for something a little bit more sophisticated. If not, don't worry. So this is the SUSY set off the UCI repo. And then we're just doing kernel ridge regression, and we take the sign of our regression as our classification label. So we're looking at 2 different values of h. And other than that, the model's the same. So the only difference between these runs is how did we approximate this kernel matrix. So you see for this larger h equals 0.15, we get comparable classification accuracy with all 3, right? I'm not trying to make any claim about 76 versus 74% here. For our purposes, those are comparable. If we go to h equals 0.07, you see that for askit, the classification accuracy goes up slightly. But for the other two methods, it goes down drastically, right? It goes 74 to 67%. And what is different there? It's only the approximation method. It should be the same model. So all we've seen is that this A2, which is the L2 error of doing a matvec, you see that this is really blown up once we get into this small h regime. So what we're seeing is if you were just using the Nystrom method and you were doing cross-validation with this model and this data, you'd say, wow, 0.07 is terrible. But you're really just seeing that my method can't approximate at that bandwidth. So that's really the main point. If you want one take-home point other than my algorithm is really scalable, it's that one. So I promised you one slide where I would talk a little bit about scalability. Just in the interest of time, would I have about 2 minutes left? 3. OK. So this experiment, we're doing a weak scaling experiment. So what that means is that we fix the number of points per core. So per compute core, there's 31,000 points. Along the x-axis, we have compute cores, number of compute cores up to 32,000, and then time on the y-axis. These 3 parts of the algorithm, the tree is just the sort of pre-processing construction of the space partitioning tree. This lighter green, that's the bottom-up step, and this yellow is the top-down step. And so you can see here, really just the punchline. All I want to do is say 32,000 cores, 1 billion data points, 144 seconds. So maybe you don't have access to 32,000 cores, but however many you have, this will probably scale to it. OK. So with that, just want to say that, I've kind of gone through a lot of things very quickly here, but the take-home points. One, we have this new method, askit, right? It's scalable, it's robust, it's efficient. There's open source code and the link there at the bottom, so please download it, try it out. 2 is this idea that's a little bit more subtle, which is that for a lot of bandwidths of interest, you wind up in this regime where global low-rank factorizations just don't work. So if you're fitting a model that uses kernel parameters, you really need to be careful in that regime. And this is where I really recommend that you at least try some runs with a method more like ours rather than one of these global factorizations. So really, your cross-validation has got to take into account these thinner bandwidths, even if they don't turn out to be the ones that are optimal in the end. Also, this askit method, it scales to billions of points, hundreds of dimensions, tens of thousands of cores. There are references at the link for that. And just to give a little bit of a teaser, currently things that we're working on is a better theory of sampling with this nearest neighbor distribution. Right now it's really all heuristic. And also direct solutions. So currently what we do is kernel metrics times a vector. And so if we need to solve a linear system involving the kernel matrix, we do it iteratively. There's a way you can extend this method that one of my colleagues is working on where you can do that solution directly. So basically you can apply I plus k inverse. So with that, please check out my website, check out my code, talk to me afterwards. Don't forget that I'm on the job market, and thank you.
Time for questions.
So what happens, do you run into issues where you get communication complexity that dominates the training or the evaluation when different data points are on different nodes and their neighbors, things like that?
Yeah, so there's not a short answer to that. I'd be happy to go over how the distributed version works later. So basically what we do is each node owns sort of a subtree of the global tree. So there's some locality among the points that one node owns.
So that assumes that you pre-partition the data.
Well, sure, but I mean, distributed tree building is an existing thing,
Okay, so
right?
So you assume you run that first.
Yeah, so you've done that first, and I mean, those algorithms exist. We didn't invent that. And then given that, you can run into problems if k is very large, and if the data are truly very high dimensional, then you wind up with neighbors that live everywhere, and you can wind up having to look at a lot of things. In practice, if there's some low dimensional structure, we don't see that.
Any other questions? So I'm not sure. You probably have an easy answer that I don't know. The nearest neighbor part, that's computationally not more complex than that?
That's quite a bit simpler than this step. So you can do...
So you have good OFN algorithms for them.
Right, so we can scale that up, and yeah. So, I mean, the short answer, what we use is just a randomized tree search. So the same kind of tree building, and then you just descend to one leaf take find neighbors in it, randomly rotate the points, do it again, and that'll converge fairly quickly in practice.
Okay. Anyone else?
So this is in practice. Sorry, this is in practice dominated by the factorization step, which is much more expensive. You're doing QR factorizations and that. So.
Okay. Thank you.